Hi everyone, this is Heejin from Purdue University. In this talk, I will introduce GPUReplay. Client devices are operating on mobile, embedded, and edge environments. They are often equipped with a powerful mobile GPU. Originally, the GPU was used for speeding up graphics rendering. However, with the increasing computation demands on client devices, the GPU is now actively used for accelerating general computation, notably machine learning workloads, such as machine learning inference and federated learning. To run GPU applications, the key is its software stack, which is in between GPU application and GPU hardware. The example of client GPUs are Mali GPU, V3D, and Adreno. The GPU stack consists of multiple layers. For the machine learning workload, it has a machine learning framework on top in the stack, such as Compute Library, TensorFlow Lite. Underneath, the stack has GPU runtime running in the user space and the GPU driver running at the kernel level. In fact, the GPU stack for machine learning workload is complex. To be specific, machine learning framework has million lines of code, and GPU runtime binary is tens of megabytes. Such a complex GPU stack makes several difficulties. The first problem is a weak security. The security issues on GPUs have been constantly reported. For instance, there were tens of CVE records on mobile GPUs in 2020. The source of vulnerabilities are stacks complex internal or the interface between layers, which is wide and diverse. By exploiting them, adversaries can lead to kernel crash or privilege escalation while threatening the integrity of GPU computation. Second, the GPU stack often shows incompatibility. In particular, GPU applications depends on specific combination of GPU stack and the operating system. For instance, Tencent's and CNN does not confirm ARM GPU compatibility on top Linux. While it requires Vulkan's API, ARM Mali supports its runtime for Android but not for Linux or Windows yet. Third, the stack leads to a slow startup of GPU application by adding unnecessary delays. For instance, launching a simple GPU job may take several seconds when it's first run. In contrast, the computation itself takes milliseconds. Such problems make it hard to deploy GPU stack. The root cause is complex GPU stack. So, where the complexity come from? The stack is fundamentally designed for the graphics workload. We found some key features for graphics in the stack. First, the compilation. A graphics application emits numerous GPU jobs, and the compiler in the runtime generates jobs when they are needed. For instance, we observed that thousands of jobs in 50 seconds of game demo. The stack may rewrite the shader just in time, as the game cannot foresee the future jobs. Second, dynamic resource management. Graphics application may have different number of jobs, consuming different size of memory. The input and data formats may diverse depending on what graphics application runs or what user action for the next rendering. Lastly, fine-grained multiplexing. It is common to run multiple graphics applications concurrently. A single application may also contain multiple GPU contexts. A window manager could be an example. To support them, stack interleaves jobs at fine intervals and maintains separation. Such a stack for graphics was not engineered for machine learning workload. Now let's take a look at the machine learning workload and see what's different from graphics. Unlike graphics, machine learning applications run predefined network requesting a small set of GPU jobs repeatedly. For instance, MobileNet consists of 28 layers and generates 54 jobs, which is fixed and repeated on each run. On top of that, on client devices, machine learning workloads often share the GPU in a coarse-grained manner. In such a case, a complex GPU stack is an overkill. So a single GPU stack has dual modalities. What machine learning workload needs is a translation from program abstraction such as high-level language to the GPU hardware primitive, for instance, job binaries. In contrast, the stack's rich functionality such as JIT compilation, dynamic memory management, or fine-grained multiplexings are unnecessary. So we introduced GPUReplay, a new way to deploy GPU-accelerated computation on mobile and embedded devices. Our approach is based on record and replay GPU computation. The developers first run record harness, such as machine learning application, with the original stack, and traces all the necessary information for GPU computation. The developers then pack all the traces into the one which is called a recording and ships it to the target machine. Then, a target device runs a replayer which loads and replays a recording. In doing so, the replayer reproduces a new computation result on its own new input. We note that as a recording has all the information, the replayer does not need GPU stack at runtime. Thereby, GPUReplay eliminates stack's problem mentioned before, such as stack's weak security, deployment difficulties, and slow startup. There are three major use cases for GPUReplay. First, the replayer can coexist with GPU stack so that the application that needs graphics rendering can still run with the original stack. The machine learning application can run without the stack by replayer. Second, the small replayer can be easily ported to the trusted execution environment where the computation integrity will be further guaranteed. The examples for case 1 and 2 are smartphone and the cloud edge node. Finally, the replayer can fully act as GPU stack in case of headless devices running without graphics interface or rendering. The examples for the case 3 would be single-purpose devices such as robot or IoT devices. This figure shows an example of a neural network execution by GPUReplay. You can record the entire network into single recording or layer by layer to the separate recordings. In this example, let's assume we have separate recording per layer. When replaying, the application starts a first layer. Then the replayer passes input data from the application to the GPU and starts interaction with the GPU. When the computation is done, the replayer returns the output from the GPU to the application. The application is now ready to replay the next layer. At this point, you can handle intermediate data between the layers, or you can also add a conditional branch to choose the next layer. For example, in case of training, you can check the result from the last layer and check if it is converged. If converged, you can just finish the replaying, otherwise keep repeating the computation. Before getting into the design details, let's talk a little about mobile GPU workflow. First of all, the mobile GPU does not have its own device memory. So in the client devices, the host memory is shared between the CPU and the GPU. When we start GPU application, the driver allocates memory for all types of data. For instance, the space for job, and the space for input and output, and also the space for intermediate data. Then the GPU runtime compiles the given GPU code to the job binary and puts into the shared memory. The runtime also copies the given input data from the application to the shared memory. In the meantime, the GPU driver constructs a page table for GPU, since the GPU works with its own GPU virtual memory. When the mapping is done, the driver populates the page table to the GPU MMU. Then, the GPU driver interacts with the GPU by register I/O and interrupt. For instance, when the input and jobs are ready, the driver kicks the GPU through register command. The GPU accesses corresponding data through its page table. When the job is done, the GPU sends an interrupt as a notification, and the application can now see the output. Then, why does GPUReplay work? Let me share some insight how it works. First is a completeness. We capture everything required for GPU computation and we pack them into a recording. Second, determinism. We identify non-deterministic CPU and GPU interactions that may result in incorrect GPU computation. We then constrain them for determinism. For instance, when recording, we force synchronized job submission to make everything in lockstep. Third, independence of input. Once you record the computation, you can get a new result repeatedly by replacing the input with a new one. Now let's take a look into some details of GPUReplay. One may have questions about what to record and replay for the completeness. Our answer is all the CPU and GPU interactions. For instance, the recorder captures every register I/O as the register I/O set up GPU to be ready for computation. Combined with the interrupt, the register I/O also manages a GPU workflow. On top of that, we capture GPU page table as it contains all the mapping information. However, we do not capture input and output and also intermediate data as they will be replaced when replaying. We only keep their address space in the page table. Then, where we can capture all those information, we put the recorder into the driver. The rationale is that it is the lowest interface between software and hardware, and thus it is aware of all the information to capture. We may choose a higher level interface for recording boundary. For instance, the interface between framework and runtime, or the one between the runtime and the driver. However, such choices require a part of GPU stack when replaying, which may lead to reinventing another GPU stack. Okay, from now, let's talk about determinism. A deterministic CPU and GPU interaction is important for the correctness of record and replay. However, we observe non-determinism even when repeating the same workload. First, we found that asynchronous job submission results in a different number of completed jobs. For instance, when the first run, the driver receives 2 interrupts, but in the second run, the driver may receive 3 interrupts. This is because of interrupts coalescing. We constrain concurrent running for deterministic interactions. In particular, we enforce synchronous job submission by limiting length of queue or injecting explicit synchronization point. Thereby, when recording, the driver submits one job at a time and receives the corresponding interrupt. Another thing that we've observed is the timing. When the driver is polling the register value, it reads the register for different times until its value is changed. For instance, when the first run, the driver reads the cache status 2 times. However, it may read the status 3 times for the next run. Besides, the job execution delay may diverge on each execution. To be specific, when the first run, the job may take 2 seconds, while for the following run, it takes 3 seconds on each job. To address it, we replace raw trace with replay actions that replayer can tolerate. For instance, multiple read register values are replaced to register polling action. We also paste replay actions not with original time interval as it may diverge. For example, we kick the GPU and synchronize the job submission with combination of register write and wait IRQ action. In doing so, the replayer can also remove unintentional delays that might come from driver's resource management, decompilation, and so forth. Now we can record a complete and deterministic CPU and GPU interactions. What you expect is when the input is given, get the output by replaying the recording. Then why does it have independency of the input? In a recording, we have a sequence of jobs. Let's look into what is in each job. The GPU job in modern mobile GPUs packs in much complexity. It has the addresses of input and output rather than their contents. The job may have multiple small jobs as a form of chain, which includes control flow and data dependencies as well. So the branch inside a job is captured when a recording time. We note that the job chains use addresses of input and output, so it is independent of the input contents. When the job is done, it stores a new output to the recorded address. However, we leave the control flow outside of recording to the CPU. For instance, when a first replaying is done, the user can use its output as input for the next GPU computation or CPU computation. Also, the user can add a kind of branch to choose what recording to be replayed next. Then, how does replayer work to reproduce computation? The replayer reads and replays a recording with a new configuration. First, it loads the page table and updates it. For example, it allocates its own shared memory and updates the mapping information with the newly allocated memory. Then, the replayer copies the captured job to the shared memory. However, it places a new input to the shared memory as the input is independent. Finally, it replaces the register I/O and reproduces GPU workflow. When it is done, the replayer extracts the output from the GPU memory to the application. We implemented GPUReplay with 2 popular GPUs, Mali Bifrost and Broadcom V3D. We add a recorder to the device driver of each GPU. While we implemented replayers targeting a variety of environments, In this slide, we present the result of user space replayer only. Please refer to the paper for more details. In our implementation, we've achieved a great reduction of code base for GPU computation. The replayer is less than 50 kilobytes with less than 1K lines of code. Compared to the original GPU stack, our replayer is less vulnerable and deployment is. The replayer is more secure than the original GPU stack because the replayer does not have a wide interface while taking predefined GPU's behaviors only. Also, by our design, the replayer does not share the GPU with other applications simultaneously. A small replayer with lower dependencies facilitates TE deployment to secure GPU computation. We measure the replayer's startup delays from the time the application is initialized to the time its first job is ready. As shown in the figure, GPUReplay reduced the startup delay by up to 98%. In our evaluation, the main bottleneck of the original stack is a shader compilation and dynamic resource management. The replayer's main source is GPU reset and loading memory dump. We also measured the inference delays of 6 networks and achieved moderately lowered inference delays. The execution delays range from 68 lower to 3% higher than the original execution. The main reason of better performance is that the replayer minimized the user-level execution and also user and kernel crossing. The replayer source is loading memory dump and pauses between replay actions. Lastly, we measure the training delays for MNIST network using DeepCL plus OpenCL configuration. On each training iteration, it runs 72 GPU jobs and 5.7K register accesses. Similar to the inference measurement, we get the faster training performance. Specifically, our replayer reduces the startup delay by 99% and training delay by 40% since it removes unnecessary delays and runtime overhead. Let me conclude the talk. The complex GPU stack creates some difficulties. The rich features of the stack are engineered for graphics, which would be overkill for machine learning workload. To handle this, we introduced GPUReplay that paves the way for GPU record and replay. We show how and why GPUReplay works, and share some insights for GPU record and replay. Our tiny replayer is portable and can be a replacement of GPU stack, since it reproduces GPU computation without stack at runtime. The replayer shows much faster to launch GPU jobs, and also it moderately improves the total inference and training performance as well. Thank you.